have a medium problem today. So we're given a graph and this is adjacent nodes list, like A, B means we have edge between A and B, and we have big list, and we want to find connected components. So but this is not simple connected components. We want to find fully connected components. Fully, I don't know if it's right. So we have like this node, we have two nodes that connected together, we have three nodes that connects each to each other, and we can have four nodes that connects all between each node connected fully to each other node. So the first way you have to how to solve it, you can use union find data structure to find disconnected components. So between groups we find just connected components with union find or disjoint set union. And this is data structure that has references in a simple array. So we have indices that points to itself initially, and that means it is a root of itself or connected component of itself. And then we have to, when we connecting with them, we just point them to different value. So just override current value of the current cell. There is optimization techniques like path compression, or we can use ranking if we want the more speed of it, but we only have 50 nodes in this lead code problem, so we don't have to use anything of that. And after the first step of finding connected components, connected groups, we have to find or count for filter only fully connected. And we have this rule that each node has to point to each other node. So basically, if we have n nodes in the group, each node has to point n-1, because this is one node and it points to other n-1 nodes. So basically group degree of each node. Degree is when you have incoming edge. For each node you can just use array, and you have to check if this is equal to group size -1. This would mean it is fully connected. So this is one way to solve it, and this is how I solved it myself. Let's look at the code. I use simple way of union find with path compression. Then I use degree array to count how many incoming edges we have, and then I use group by to find to group only by the roots and have group and group size. And then I use this basically inside the group, all the items degree should be equal to group size -1. This is how it is accepted solution, but we can do better actually. Let's look at the better solution. This is let's look at the problem. It's only 50 elements, That means we can fit something into 64-bit variable or long in some languages like Kotlin. Basically, for each edge, we can just use this 64 bits, and for example, this is edge or node 1, and if it points to other nodes, we can just use bits, like bits positions. 1 shift left the node B. For example, if we have node 1 connected to node 3, we just use this matrix of 1. This would be a single long variable, long, and we do bitwise operation OR to set the bit, and then use 1 shift left this 3, and 1 shift left 3 is 2 to the power of 3 or 8, but this doesn't matter in this case. So basically, for each node we can have these good looking long values that has some bits set, and if we set the node bit itself, then for each other node in this group, they connection matrix long would look the same. So basically we have these long values, like long, long, long. For each it is a adjacency matrix, like we have bits 50 by 50, and for the node X, if we have connected them to node Y and node G, we have this as 1 in the intersection of X row and Y column or G column. And if we set the X 2, then we have this single long variable, single long value that would look identical for the Y and for the J, because they all set the bit. So X and Y connected, X, Y and Y connected, and Y and G connected if they are in the same group. And we just check that. So if we then filter by this long counting unique, then we have to the answer for what the group count, and we can check the size of the group. Size of the group should be equal to the bits count. Let's look at the code for this. This is Rust, and I use this initialization of the adjacency matrix with ones for each value, for each position, and then I use fold to set the bits and in the connections. Then I use counts and check that counts equal the number of bits, and then I filter to count how many groups we have with this property. And now let's look at the Kotlin one. This is the Kotlin one, same fold long array, and then group by count 1 bits. Okay, that's it for today.